Hello, I'm Rafael and I'm presenting an introduction to concurrency specifically focused on the Linux kernel. And after that, I'll review a paper, a really interesting paper that focuses on concurrency bugs on the Linux kernel. So, what is concurrency? For we using computers, this feels like parallelism, but it's not the same thing. Initially, computers didn't have multiple CPUs, so the operating systems use the time-sharing technique to put multiple tasks running one at a time, but you run a bit of one a bit of the other, and you have a sensation of parallelism this way. Which this is the first the example in the first column here. We have two tasks, one executes at one time, the second executes after that, and we can interleave these, leaving the impression that they run in parallel. But nowadays we have multiple CPUs in a cell phone, so we actually can have parallel programs. If we can run multiple programs in a single computer at the same time, we can also use this to accelerate a program. If we have a complex task, we can cut it in multiple small pieces and run them in parallel. This can be really useful to scale applications, but unless those tasks are completely separate from each other, we eventually will need to unite the results, or we have to use shared memory at all steps. This can cause issues. If we don't control how we access and write to shared memory, we can lead to deadlocks, which are complete blocking our system, our program. Or even worse, we can have silent bugs where the program seems to be working, but the results will be wrong because different threads, different processes are accessing memory and they are not using the correct techniques to control this. I have here a really simple example of a bug like this. Here we are accessing a counter and incrementing. It's a pretty simple task. Here in task 1, we read the value x, it's 1, we incremented it 2, and then we write it 2. It stops. But thread 2 is also running in parallel, and it reads the value 1 before thread 1 writes the value 2. So it reads 1, and then it increments 2. The result is 2, while we expected the value 3, because we have two threads reading the same counter. How we control that? We have various techniques. I'll explain some of them in the next slides. But what I want to focus here is there are techniques in user space, and there are some things that make it more complex in the kernel because we have interrupts and preemption. But before going forward, I need to introduce three concepts. First, context switching. What is it? When I said earlier that we can have one task executing and then go to another and then go back to the first one, this is context switching. The CPU needs to have all those registers that it's using for the first task set in place for when it's going to return to this task. And then the CPU actually needs to copy all these registers into memory and copy all the registers from the new task that's going to execute into the registers themselves so it can run the task expected. And eventually you do the opposite and replace the registers with the old ones. This has a cost. Usually we don't care for this in user space, but in kernel there are some really sensitive parts that we need to look for it. Interrupts. What are interrupts? When we press J on the keyboard, the computer receives an interrupt from the hardware. It's a signal that a CPU needs to stop what it's doing to read the signal to collect this data, in this case a keyboard press, and store it in a buffer somewhere or use it for something. Well, but this caused a context switching because it had to preempt a task to start processing this interrupt and then return to what it was doing. And I already explained what preemption is. It's this removal of a task to complete it later. It could be removed in the middle of something. Preemption can also come from software. The scheduler can do the same thing. It can decide that I'm not going to work on task 1 anymore, I'm now going to work on task 2. All of these concepts come back to context switching, because to do preemption, the CPU will do some context switching. Interrupts also cause context switching. In the kernel, one of the techniques is locking for controlling this, controlling memory access. And in the kernel, there are 3 kinds of locks. First, spin lock is the most simple, the most lightweight. It is basically the CPU looping around and checking, is it my time to execute? Is it my time to execute? And it only stops it only stops spinning when it's time. And there's no sleeping, no context switching involved in this one. That's why it's so lightweight. It should be used when we know this waiting is going to be short and we don't want to introduce extra costs or extra or even time into this lock. The sleeping locks are the ones we are most familiar with in user space applications, for example, mutexes and semaphores, and those involve context switching. When we call us a mutex and we are trying to acquire a lock and it's not available, this task will sleep. The CPU then will switch context to execute something else, and then only after that lock is available, it will return to that task it was doing before. Lastly, there are CPU local locks. In the kernel, we have some data structures that are specific for each CPU. This is one of the use cases, but we also have some locks that are only there to prevent interrupts from happening. There are also lockless synchronization algorithms. RCU, it's really interesting, but it's quite complex in the interface. But the simple explanation is we are not blocking anyone, but we are ordering how reads and writes occur. So it's RCU read, copy, update. All readers that are accessing a space in memory will continue, but the writer will write to a new position in memory and then swap the pointers after those readers that were reading before the write occurs. And this can introduce at most a bit of delay, but it doesn't block anyone. Atomics are a usually hardware feature. There are CPU instructions that guarantee a write and a modification will happen at the same time, so we can read and change the value in one call. And this guarantees that conflicting operations won't happen at the same time. There are also bugs that can happen because we are freeing memory in different threads. So if we are sharing memory, eventually we need to free memory, otherwise we will have memory leak. But if we try to use memory that was freed, we have use after free bugs. And reference counting is another lockless synchronization technique that we guarantee the memory will be freed, but only when the last reference to that space of memory is actually dropped. That's why it's called reference counting. We count who's referencing it and eventually we drop it. And lastly, there's memory barriers, which is also about ordering read and write, and I'll explain in details later. To bring up the interrupt bug a bit, this is a figure from the article we are going to talk later, and we have actually two possible bugs in this case. But first, the interrupt bug. Here in thread A, we acquired a lock. Here in red is the original line, and in green is what it was changed to. The original one here just acquired a simple lock, and this lock does not prevent interrupts. The one in green prevents interrupts from happening, but the red didn't. And then an interrupt happened, and the code inside the handler for that interrupt acquired a lock too. And now we have a lock on domain and IOMMU, but this caused a deadlock because we are both waiting for locks in and the structure is locked. The other bug here is, well, if this were two threads in different parts of the code and they were accessing the two same blocks of memory, if we actually lock them in different orders, like we have here, first IOMMU, then domain, and here first domain, then IOMMU. We can have a situation where the first one will acquire successfully a lock on IOMMU, and then we'll be stuck waiting for domain because someone already got the lock for domain, and it is stuck waiting for IOMMU. So we have the two threads locked, waiting for someone to release the lock, and no one will. So we have a deadlock too. Now, going back to memory barriers. There are two kinds of memory barriers. They are the same, but one focusing on how compilers deal with our code, and the second one how the CPUs themselves handle the instructions we give them. And on the kernel, we usually have this in read once and write once calls, and some, depending on the architecture, even the atomic calls need these barriers too. How this actually works. Here in the left, we have a example code written in C that uses uses atomics and uses a spin lock too, and no memory barriers yet. These two variables here are the spin lock. Current is the task that's being executed now, and line is the line of tasks to be executed. Actually, it's a ticket spin lock, and here in line 11 our function is retrieving its ticket. We are using an atomic function that retrieves from memory and adds 1 to it in the same instruction. This guarantees even if you have many functions calling the same thing, each one will only have its individual value. We won't have the same value for different functions. Then ticket is my place in line, and it will go into this loop waiting for my place in line. Is the current one my ticket? And if it's not, it will keep looping around. So it's not sleeping, it's just burning CPU cycles waiting for its time. When eventually it comes to ticket being the current, or it means it's my turn to run, then I can run whatever I want to run. In this case, it's a generic compute function that operates on shared value. This shared value is the shared memory that we need to protect. After this, we're going to release the lock. How this is done? We just add 1 to this ticket and save it to current. In other words, it's time for the next one, and someone else will come to the same conclusion. Oh, now it's my turn, and run after I release this. And how this is compiled to? Well, it's quite one for one here. It's really simple. First here, the atomic operation taking this appending 1 and get my tickets. Here it's the loop. It compares these two registers, and while this comparison is valid, it will keep looping, and eventually it will be different, and we will come out of this loop. And then we call compute, save the value to shared value. We add 1 to the ticket, saved it to current, and the lock is lifted. However, this is using GCC with 01 compiled optimization. This is level 1 of the optimizations. What if we tell GCC to optimize a bit more? Can you tell the difference? Well, the compute, the order changed. Here in optimization 2, CPU decided, well, we can call compute, but since we want to add 1 to this ticket and save it to current, and I already have this in memory, this is already in this register, it's really close to me, I can do this before actually saving the value from the compute function. This already broke our system, because now we just released the lock before saving the shared value. Then if it's shared, so the next one who's calling will either override it with new value, or even the compute will be wrong, whatever. Memory barriers are a way to tell the compilers that this cannot happen. The order we wrote here needs to be kept in the compiled version. The memory barrier here is a software one. It's just for the compiler. We are introducing an empty assembly instruction in we're telling the compiler that this touches memory. What this means, the compiler will not try to change order here. So here we have the same code with O2. The resulting assembly is the same. There's no new instructions added here. The compiler completely dropped this memory barrier here, but the result is correct. Using O3, it's the same thing. And okay, but this is about the compilers. I just told you that hardware does the same thing. What happens is the hardware can decide to not do all the reads at the time you wanted, or even the writes. It can just keep a buffer for reads and a buffer for writes and eventually do them. For hardware, we need to introduce a new instruction, which in this case is mfence, which is it's a memory barrier for the CPU itself. And here we have a difference in the resulting assembly, which we have the instruction added here. But the result is the same. We just tell the CPU, hey, when you get to this one, clear your buffers, do all your reads that you are pending, do the writes you are pending, and only then continue. Then here we guarantee this write for the line 10 was done at this time before we actually do the reading in. Actually, it's a write again, right? But we actually before we do the write here for the current in the spin lock, and this prevents the next read from the next compute from the next thread to read the value before we actually wrote this value to memory. Okay, how can we find these bugs in the kernel? Those are complex bugs. They aren't usually picked up by static analysis. Those who are usually fixed quite fast. And then we go to dynamic analysis. KC-SUN is the most, this is the current active dynamic analysis tool for concurrency bugs. However, it's not usable in production. I deployed it to my computer and it's got really slow. What it does, it uses sampling for 1 in every 2,000 accesses. It introduces some delay. It monitors the variables that they were using. And here in the right, we have the example of a error report this tool can generate. This is from the kernel documentation. Here it says, we had a write for this address. This is the stack trace for this write. We had a read for this address. Here's a stack trace and the value changed. And we can use this to read the code and try to understand what went wrong. Do we need a new synchronization call here? Maybe it has a synchronization call, but we need to change it. Maybe it's not being used correctly. This is how we can fix them. And now I'm going to talk about the study as I said before. This is really recent. It was published in a convention, the ICSE convention in Rio de Janeiro, Brazil, and it is really interesting. It's a comprehensive study on concurrency bugs in the Linux kernel. What were the researchers' methodology? First, they decided to create a data set of concurrency bugs from the kernel. They focused on the mainline. They took a random sample of bug fixing commits. They filtered them with keywords, and then they did some manual validation to guarantee this filtering is capturing all the bugs in this 100 commits. They validated manually how many of those 100 commits were concurrency bugs, and the selection passed the test. It correctly captured all the concurrency bugs, but it captured more, so we need to do some manual analysis after that, which is the step 2. We have a systematic analysis. We have 2 researchers independently reviewing every commit that was captured by the system, and after that we have a joint discussion where we analyze and we resolve what the researchers come to a different conclusion. The bug selection focused on mainline, as I said before, in the period from January 2019 to June 2023. These here are the keywords they used to filter it, and it resulted in 1,633 commits filtered. And those they had to manually analyze, and they came to 200 confirmed concurrency kernel bugs. Analyzing this is quite hard. 200 is a really large number actually, because they have to have a lot of time to analyze each commit and the discussion in the mailing list, and they need to understand the kernel to confirm those are concurrency bugs. What they were analyzing for each bug. First, what is the manifestation condition? Did it depend on interrupts? Could it be discovered in virtual machines? Is it hardware specific? Does it depend on a specific driver? For what subsystem in the kernel it's applied to? And about the root cause and bug pattern. They were trying to understand if those bugs were atomicity violation or order violation, if it was a deadlock. And what was the cause? Was it a misuse of a synchronization primitive? Was it maybe the lack of a synchronization primitive? And lastly, how was the discovery and repair for those bugs? Was it discovered by an automatic tool? Was it discovered manually? Was it fuzzing? Or maybe it was undeclared? And about repairing, they were interested in the time it took for repair since the discovery and how complex was the fix. The results here are really interesting. 71% of the bugs were thread related, but the very non-significant 27.5% of the bugs were depending on interrupts. This is even more significant because the authors argue that there's a lack of exploration for this. We are mostly looking for thread-related bugs, and apparently no one's looking for interrupt-related bugs. 44% of those bugs were in drivers, and 69.3% of these driver bugs were in control paths. That is, usually opposing operations, like driver initialization versus driver reset. And from this, we can actually use this to focus our analysis and maybe try to find good insights in these cases. 45% of the bugs won't happen in VMs. From this, they just take that, well, we need to improve our techniques, either analyzing these bugs in hardware or improving how fuzzing technologies work, or how our current VM techniques work. 24.5% of the bugs were deadlocks, and 32% of these bugs could happen on single threads. This is something that usually we don't see in user space programs because we don't have interrupts, and interrupts are the cause for these single threaded deadlocks. 90% of the non-deadlocked bugs were atomic or order violation bugs. This is quite similar to user space, and here we can just keep using the same techniques with just minor considerations. 29.5% of the bugs were due to synchronization technique misuse, either a wrong choice of technique or a missing part of the technique, like we have an mutex but we don't have the initialization correctly. This highlights that choosing the correct technique is hard. It depends on the subsystem. Maybe some developers have their preference, but the context matters a lot. Lastly, 98.5% of the bugs happen on 2 or less threads. This means while it's possible for bugs to depend on 3 or more threads, but this time it's an insignificant value. We should focus on looking at 2 or less threads. About finding and repair. The researchers only found information for 85 of those bugs. They looked at the mailing list and they looked at the discussions, but only 85 of those had information attached. And from those, 34.1% were found by automated tools. That's too little. 65.9% were found manually. And then we can use this as a call out. Let's try to improve those automatic tools to find more bugs for us. From the time it takes to fix those bugs is also quite larger, and the resulting patches to fix them is more complex. We have 1.9 times more insertions in those patches, and usually those insertions aren't on single blobs. They are usually more scattered than fixes for normal bugs, and this makes it harder for review and for fixing and for the reviewers, which is a critical part of the Linux kernel. The maintainers need to review every single patch, and reviewing these bugs is more complex too. The researchers would like to also highlight the prior work. The first one here is really important because it uses the same process, the same methodology, but only analyzing user space software. They use Apache softwares, MySQL, and Firefox, for example. The other two here were analyzing the kernel, but focusing on a specific kind of bug. The first one, data races, and the second one, the use after free bugs. But still, those are also really interesting work. The conclusion these authors came to is, well, concurrency in the kernel is fundamentally different from user space. And because of this, well, we have the interrupts, we have harder dependency, and we have more kinds of synchronization patterns to work with. And we then need to have better techniques specific for the kernel to address these bugs, either for finding the bugs faster, to solving them faster, and well, we need to help the community with this. That's it. Thank you.